In this video, we will be looking at a few equilibrium calculation questions. Let's take a look at this question where bromine gas dissociates to form bromine atoms. We are given the starting number of moles of bromine and the volume of the container, as well as how many percent undergoes dissociation. Then we are supposed to calculate the equilibrium constant for this reaction. So for this question, let's first start off by drawing the ICE table. We are given the starting number of moles of bromine and the volume of the flask. So from this, we can calculate the initial concentration of bromine. So take 1.9 moles and divide by 0.9 liters. And we will get 2.111 molar. We are also given the information that 1.40% of the Br2 undergoes dissociation. So we can calculate the change in bromine concentration. It will be 1.4% times the initial concentration, which is 2.111. And we will get 0.0296 molar. So let's put the values that we have into the ICE table. We have initial bromine concentration of 2.111. Initially, there are no bromine atoms, so this would be 0. Change in Br2 would be 0.0296. Since Br2 is dissociating, the change will be negative because the concentration of bromine will be decreasing. Whereas for Br, the concentration would be increasing, so the change would be positive. Let's look at the stoichiometric ratio. The stoichiometric ratio of Br2 to Br is 1:2. So the change in the concentration of Br will be 2 times 0.0296, but with a positive sign because it is increasing. So it will increase by 0.0591. Now with the initial and change in concentration values, we can calculate the equilibrium values. So 2.111 minus 0.0296 would be 2.0814. And for bromine atoms, 0 plus 0.0591, you have 0.0591. So these are the equilibrium concentrations. Now we can calculate the equilibrium constant. So Kc equals to Br atoms to the power of 2 divided by Br2. So let's substitute the values in. So here we get the answer for Kc as 1.68 times 10 to the power of negative 3. Now let's look at another question. In this question, you are given the Kc value and you are asked to find the concentrations of H2, Br2 and HBr at equilibrium. So let's start off by writing our ICE table because that's how you're going to calculate the concentrations at equilibrium. Let's look at the information given. You are given the starting number of moles of HBr and the volume of the reaction vessel. So from there we can count the initial concentration of HBr. So based on these values, we have an initial concentration of 0.07547 molar. Let's put this value into the table. There is no hydrogen gas or bromine gas at the start, so the initial concentrations for these two gases would be 0. Now to fill up the change in concentrations, we don't have any exact values to put in, so let's represent it as X. Let's look at the stoichiometric ratio of the gases. H plus to Br2 to HBr has a 1:1:2 ratio. So we could represent the change in concentration as X, X, and 2X. But there will be a difference in the sign. So since we start off with HBr, the concentration of HBr will decrease because it will be dissociated to form H2 and Br2. Whereas for hydrogen and bromine gas, since it is being produced, then the change will be positive. So equilibrium values will be X for H2, X for Br2, and 0.07547 minus 2X for HBr. Another piece of information we are given is the equilibrium constant, Kc. So let's first write out the equilibrium constant expression. So based on the equation, Kc equals to HBr concentration to the power of 2 divided by H2 and Br2. Now let's substitute the values in. Now taking the square root of both sides, we get so we can find out the value of X, which is in this case 5.11 times 10 to the power of negative 5. So now looking back at the concentrations of all the gases at equilibrium, we can say that concentration of H2 at equilibrium is X, which is 5.11 times 10 to the power of negative 5 molar. Similarly, concentration of Br2 is X, which is 5.11 times 10 to the power of negative 5 molar. And for HBr, we have to do the calculation. And we will get 0.0754 molar. In this question, once again, we are given the equilibrium constant and we are asked to calculate the concentration of each species at equilibrium. So let's start off by drawing out the ICE table because this is something that we will need to calculate the concentrations at equilibrium. We are given an information that there is 0.88 moles of hydrogen and 0.88 moles of carbon dioxide initially, and we are also given the volume of the flask, which is 4.7 liters. So let's calculate the initial concentration of H2 and CO2. Now let's put these values into the ICE table. Initially, there's no H2O and CO, so let's put the initial values as 0. For now, there's no more information that we can fill up into the table, so let's represent the change in concentration as X. So let's take a look at the stoichiometric ratio. In the chemical reaction, H2 reacts with CO2 in a ratio of 1:1, and the ratio for the products is also a 1:1 ratio. So the change can be in terms of X, but for H2 and CO2, they will be decreasing, so the change will have a negative value, whereas for H2O and CO, these are products, so their concentration will increase and therefore the change will have a positive value. So now let's write the equilibrium concentrations in terms of X. So now let's make use of the equilibrium constant that's given. First, let's write the expression for Kc. So Kc would be the concentration of the products raised to the power of their stoichiometric coefficients. So that's H2O and CO. Divide by concentration of reactants raised to the power of their stoichiometric coefficients. But in this case, the coefficients are all 1. So let's fill in the values that are given. So now taking the square root of both sides, we get this expression. So now let's solve the equation. So now that we have the value of X, we can calculate the concentration of each gas at equilibrium. Since the initial data is given in 2 significant figures, we can round this to 2 significant figures. So these are the concentrations in 2 significant figures. Now let's take a look at this question. A quantity of specific gram of SO2Cl2 was placed in a flask, and then at 648 kelvins there is 0.0345 moles of SO2 present. So first of all, it may not seem very obvious, but the 9.75 grams of SO2Cl2 is the initial amount, and the amount of SO2 is actually the equilibrium amount. So let's get this clear first before we do the calculations. For SO2Cl2, we are given the amount in terms of the mass in grams, So before we do any other calculations, we first have to find out how many moles this is. So to do that, let's first calculate the molar mass of SO2Cl2. Referring to the periodic table, we can calculate the MR, and it is 134.969 grams per mole. So now that we have MR, we can calculate the number of moles. We are given the volume of the flask, which is 2 liters. So we can calculate the initial concentration of SO2Cl2. With the data given, we can also calculate the equilibrium concentration of SO2. So now let's do up the ICE table to find the equilibrium concentrations of all the gases. We have calculated the initial concentration of SO2Cl2, so let's put that in. Initially, there's no SO2 or Cl2, so initial values are 0. And we also know the equilibrium concentration of SO2, so let's put that in. So now we can calculate the change in SO2 concentration. Okay, just take the equilibrium concentration minus the initial concentration to get the change. Now let's write the change in concentration for the other gases. So to do that, let's look at the stoichiometric ratio. The ratio of SO2Cl2 to SO2 to Cl2 is 1:1:1 ratio. So the amount of change will be the same. For Cl2, it will increase because Cl2 will be produced by this reaction. As for SO2Cl2, it will be used up, so the change will have a negative sign, but the value is the same. So just to reiterate, the value is determined by the stoichiometric ratio, so all of them will change by 0.01725 because all of them are in a 1:1 ratio. But in terms of the sign, the products that are being formed will have a positive sign for the change, but the reactants will have a negative sign because they are being used up. So now let's calculate the equilibrium concentrations. Alright, now that we have the equilibrium concentrations, we can calculate Kc. So let's write the expression for Kc. Kc would be the concentration of the products, SO2 and Cl2, raised to the power of their stoichiometric coefficients, which is 1 each, divide by concentration of the reactant, that's SO2Cl2, and also raised to the power of 1. So let's enter the values. And we can round the answer to 3 significant figures.